Oh hi, didn't see you there. The history of the golden ratio began in ancient Greece. No one properly knows who first discovered the golden ratio. However, notable Greek users include Pythagoras, who is now known for his work around the side lengths of triangles, Hippocrates, Plato, and Phidias, who used the ratio in his sculptures for the Parthenon. After the ancient Greeks, the use of the golden ratio in aesthetics disappeared. It wasn't until the Middle Ages where it picked up again, most notably by the man whose name is immortalised in his work, Fibonacci. Throughout history, the golden ratio has been used in art. During the Renaissance period, it is speculated that Leonardo da Vinci used the golden ratio in some of his artwork, due to his views that some bodily proportions actually use the golden ratio. Salvador Dali even used the golden ratio in his masterpiece, Sacrament of the Last Supper. Today, the golden ratio has even spread to the motor industry. If ever you wondered why the Aston Martin DB9 is such an aesthetically pleasing car to look at, you might be surprised to find out that its design uses the concept of the golden ratio.
One way to prove the relationship between the Fibonacci sequence and the golden ratio is to apply the formula of the golden ratio to the Fibonacci sequence. So the Fibonacci sequence is when the first number added to the second number gives you the next number in the sequence. So 1 plus 1 equals 2, 2 plus 3 equals 5, and so on. The equation of the golden ratio is A plus B over A equals A over B, which will then give you 1.6180, or the golden number. So in this formula, A, in a line, A represents the longer part, and B represents the shorter part. When you apply the Fibonacci sequence to this formula, and it equals 1.6180, it proves the relationship between the two. Let's sub in 144 and 233 as our numbers. So if A equals 233 and B equals 144, then 233 plus 144 over 233 should equal 233 over 144. If we put this into the calculator, we find that it actually does, and the answer is 1.6180 on both sides. This is therefore proving the relationship between the Fibonacci sequence and the golden ratio. The best way to draw a perfect rectangle using the golden ratio is to first start with a perfect square. Let's make each side length worth 1. If we mark the halfway point down the bottom, so this is worth half, and then we draw a diagonal line across to the corner of the perfect square, like that. Now we just have to rotate this line down so it's horizontal with the base of the square. And then we can just finish drawing the rest of the square. And then if we round out just the middle part, that gives us our perfect rectangle.
Oh, sorry, didn't see you there. The Fibonacci sequence appears everywhere in nature, across both plants, animals and other kingdoms. It appears in plants over many examples, including the patterns of florets of a flower, the bracts of a pine cone, or the scales of a pineapple. Plants do not know about the Fibonacci sequence. They just grow in the most efficient way, coincidentally followed. Animals are also closely related to the Fibonacci sequence. Some examples include the bone sections of human fingers and human forearm to hand that follow the golden ratio. In the seeming randomness of the natural world, we can find many instances of the mathematic order involving Fibonacci sequence and the closely related golden ratio.